Hello scholars, welcome. Mr. Hinkle here. This discussion is going to be about the rise and the fall of the ocean that happens multiple times a day on every coastline, everywhere in the world. You guessed it, the title is up there. We're talking about tides. So, objectives: explore the connection between gravity, it's the key player, and tides, and then discuss various types of tides. Here's the things: tidal day, tidal range, and classification of our tides. Let's do it. So I love this image. There's water and boats. There's boats but no water. What the heck happened? This is within a 6-hour period even in the Bay of Fundy, where the difference between high tide and low tide, the tidal range, is the greatest. But tides are the periodic rise and fall of ocean water. They happen because of gravity. Gravity between the Earth, the Sun, and the Moon. And we need to understand tides for understanding how coastlines work, how to navigate, and when to go out and play, recreate in these coastal areas. So here we go. Tides exist because the Earth, the Sun, and the Moon have gravity. Moon is the most important player. The Sun is the next most. The Earth is covered with water. 71% oceans, 29% lands. And circling our Earth is the Moon. Now, the Moon's gravity exerts an influence on the oceans that creates a tidal bulge, and it pulls Earth's water towards it, and then the water on the other side actually forms a bulge also. As the Earth rotates, once every 24 hours, we know this, we wake up, the sun is out, we go to bed at night, 24 hours a day on our clocks, got it. As the Earth rotates, what actually happens is the Earth rotates in and out of the tidal bulge. So this point on Earth is in high tide, rotates 6 hours, it'd be behind the board, low tide, rotates another 6 hours, it's on this side, high tide, rotates, it's out here, I'm doing 3-dimension, low tide, and then rotates back, high tide again. So we can see the lunar bulge because of the Moon's gravity and Earth rotating in and out of this bulge. It's pretty amazing that the Moon can exert such a force. Now, the Sun also plays an important component, but the Sun's gravity doesn't play as big a piece on tides as the Moon does because of the distance. Newton's law of gravitation, there's a gravitational constant. It's the mass of the first object times the mass of the second object over the square of the radius, right? Force of gravity equals G m1, m2 over the radius squared. Now, if you're like, what the heck are you talking about? What's important to know here is it's the inverse over the square of the radius. So even though the sun is way bigger than the moon, when we look at how far the sun is away, this r squared, because this is the r here between the sun, this is the r here between the moon, the r for the sun makes the force of gravity of the sun exert a lesser influence than the moon. Okay, so we got 3 key players. We got the Earth, we got the Sun, we got the Moon. We got Earth's water being pulled in various directions because of these influences of gravity. And what happens is we get the Sun, the Moon, and the Earth resulting in what's called syzygy. And syzygy gives us spring tides. When the Earth, the Sun, and the Moon are all in line, we get the highest high tides. Now, let me see, do I have, yeah, great. I got a whole another slide on this that I want to talk about. Let's bring the sun in. When the sun, the earth, and the moon are lined up, and the moon could be on either side. When it's on this side, we see it. This is the full moon. Over here, no moon, quarter moon. Down here, quarter moon. So the biggest tides are going to occur, the highest high tides, when the sun, the moon, and the earth. This happens every new moon and every full moon, and these are our spring tides. The movement of celestial bodies influencing what's happening at coastlines on Earth. I love this. Well, what happens when the moon is in quarter moon? First quarter or third quarter? Well, you get the lowest high tides because the effects of the moon and the sun essentially cancel. So here's a spring tide. Here's a spring tide, quarter moon. These are neap tides. Every month, there are 2 spring tides and 2 neap tides. And the height of the tides changes with the phases of the moon because tides are dependent on the location of the Earth and the moon, and to a lesser extent, the sun. So the Earth day is 24 hours, but every 28 days the moon orbits the Earth. And so as Earth does one full rotation, the moon is moving also. So the tidal day is 24 hours and 50 minutes because it takes that long to get to the same location with the moon directly overhead as it did the day before. The lunar day and the solar day on Earth are different. The solar day is Earth rotates once to get with the sun in the same spot, 24 hours. The lunar day, the Earth rotates, but the moon is orbited 24 hours and 50 minutes. This is our tidal day. Back to the Bay of Fundy. So we can look at the difference between the high tide and the low tide, and we can call that difference the tidal range. Tidal range can be extreme like the Bay of Fundy in Canada, or in places in the Mediterranean Sea it's 10 centimeters. Now, this is because we have an ideal, right? I've just been drawing things on the board up here. We have ideal conditions, and then we have real world conditions. And in the real world, we have coastlines, and we have continents, and we have ocean currents, and we have storms out at sea. So the actual tides that we see on Earth are extremely variable as to where we've been talking about idealized tides. Now let's talk about real tides. Continents, friction with the seafloor, modify the tidal bulge. Tides are force waves. They're not freely propagating due to being pulled by gravity, and the idealized bulges cannot form. So here is an actual tide chart from Monterey for a week in the month of March, where we see high tide, low tide, oh, high, little low, high, little low, high, real low, high. So different tidal ranges at different parts of the week. Actual, real tidal data. But what we do see, the periodic rise and fall of tides. Now, real tides are classified into 3 structures. We've got diurnal, where we have 1 high tide and 1 low tide every single day. We have semi-diurnal, where we have 2 high tides and 2 low tides every single day. And then what is most common is 2 high tides and 2 low tides, but they're not this perfect sinusoidal wave, they're actually mixed. The tidal range differs on different days throughout the period, and this is because of all of those reasons that we just mentioned, because of ocean currents, because of friction with the seafloor, because of the variable topography at certain coastlines. And so mixed, and this is what we saw here, this is a mixed tide classification. Okay, cool. Tides are awesome. When the tide is low, you can go out and you can look at all the cool benthic organisms, and you can go tide pooling and stick your finger in sea anemones. And when the tide is high, you can't do that, but then maybe you're swimming in the ocean. So understanding tides helps us to really know how coastlines function, and it also puts our Earth in perspective, in connection with the moon and the sun, because tides are the rise and the fall of ocean's shoreline at coastlines because of the gravitational effects of the Earth and the moon, and to a lesser extent, the sun. So this is our intro, brief understanding into tides. Thank you so much, and I'll see you again.